In this final part of the introduction unit, I would like to first wrap up what you have learned so far in this unit. We have started with an overview over Lagrangian methods, and you have seen that they are used for many different purposes and applications, ranging from particle tracking, as with the discrete element method, to molecular dynamic systems of materials. All these Lagrangian methods are of extremely high value for industry and the engineering disciplines. Think of studying particle processes or the engineering of materials, so the design of materials, for example, and many more other applications. For example, simulation of fluid flow, simulation of pastes. You have seen that the discrete element method is one variant of a Lagrangian or discrete method, and that the DEM follows relatively hard particles in a fluid flow, or even it works without a fluid, of course. Sometimes the DEM is used for droplets or bubbles, but this is more a niche application. The key values of the discrete element method are that you can obtain per particle information. This is very hard to get with experiments or other methods, for example, an Eulerian method. You can consider easily different particle sizes. You will see that this is not so simple if we have extremely different sizes, but in principle it's possible. Again, doing that with an Eulerian method is very different, and also experimental approaches to measure the local particle size, for example, are relatively expensive. Last but not least, one can consider other physical aspects with the discrete element method, since we follow particles, and these are, for example, the temperature of particles, the melting behavior of particles, or for example the moisture content of the particle as it changes in a dryer, for example. All this makes the discrete element method ideally suited for engineering applications like chemical engineering studies, where we are interested in the performance of an industrial process. What would be the logical next steps when you watch this MOOC? Well, first, try to seriously follow the MOOC and gain your badges. The badges are important because it is a check for you whether you have fully understood what happened in the part of the MOOC or not. Also, recommend the MOOC to others. Maybe they're also interested in that. And third, I also recommend you, in addition to doing the MOOC, to dig deeper into the discrete element method, for example, by installing software. Note for that you might need help from other people, and you might also want to start reading books about the discrete element method, and I will show you a selection of them later on. Also, if you are at the university or you want to further promote the MOOC, please feel free to adapt this MOOC's material for your own course or for your own teaching exercises. With that, I would like to now come to the reading recommendations. Further reading, there is an excellent full course on DEM by Voskrin and Sarkar. It's already from 2008, but it's freely available and it's very useful. It gives you a lot of details. Then there are very good books about the method. For example, the book of Norouzi et al. That is from 2016 in John Wiley and Sons. There is an excellent book of Pöschl and Schwager on the computational aspect of different methods, and one of the methods that is presented in this book is the discrete element method. And last but not least, broader background is presented by Crow et al. In this excellent book. Additional teacher information. How could you integrate this MOOC into your own work? Well, first, you can just do a MOOC, of course. That's okay. You can adapt the MOOC material if you want. That's also fine. But if you want to combine it with classical teaching, you can design it like this. For example, you give the students an a MOOC at the very beginning. This is starting the MOOC, this is ending the MOOC. Then you have a quiz at the end of the MOOC. That can be, for example, the quizzes that you have as a part of this MOOC. And then you do classical in-classroom teaching with a final examination. So this is would be the variation called Intro MOOC. It's very nicely described by these publications of my colleagues. Unfortunately, this is in German, available only, but I think the images are enough. So this is one option. The second one would be that you do a so-called inter-MOOC concept, that you have the MOOC between multiple classroom units and at the end of the examination. And a third option would be, very innovative option, to have a so-called inverse blended MOOC, where you enrich the MOOC, the online content, by in-classroom units or even by group work. So this turned out to be a very successful, innovative concept, how to combine the MOOC with in-classroom or group work.
I hope you have enjoyed the introduction to this MOOC and are now motivated to go through the individual units of the discrete element method MOOC.